I'm going to exercise is with this method. This method is saying we will be able to calculate the diffraction by taking the partial derivative of U, the strain energy, respect to where the loading applied at that location. And so from here we see that is the skills, that will be the tip to help you. So for this question, let me readdress the problems here. So this is the loading we applied. But however, for this case, what we're looking for is a diffraction at here, where there's no loading given by the problem. If we want to exercise the theory, we must have the loading being built up at where we want to calculate diffraction. Otherwise, that theory won't go anywhere. So the principle is this. We add one virtual load, and then during our process, we're going to set up, for example, here, let me say the virtual loading. In our calculation process, we're going to set up Q equal to 0 to where that is appropriate. Because we introduce additional symbol Q, which we can visualize, we can treat it as a variable, and then imagine the whole strain energy will contain and be the function of P and Q. So we'll be able to do the partial derivative with respect to this one, and then we're setting up that value equal to 0 to set them to somewhere. So you see, so using this principle, then we apply the theory is this. The delta D per that theorem is U partial derivative respect to Q, okay? And because Q is virtual, which means virtually is value equal to 0, so we calculate this one at this value equal to 0. That would be the applications of this formula. So again, the tip is this. If you want to calculate the diffraction where the loading not given, you have to introduce by yourself an artificial loading and setting up that artificial loading equal to 0.
But is that only if you only have one loading? So that way if you had like two loading, you wouldn't actually introduce?
So again, we're back to this one. We're back to this one. In our traditional method, this formula can be okay. It's okay to calculate the diffraction at where the loading applied. If we want to calculate using this method, if I want to calculate the loading at here, this won't apply, right?
Okay.
This method only applies to where the diffraction at where the loading. If we want to calculate this one, then you can see, if we want to calculate this one, then we have to utilize this formula by introducing additional virtual loading Q's similar to this one. Then we apply the same formula to apply to this point and setting up Q equal to 0. That is the overall, that is a top, very top concept. Yes.
So if you given a single loading, but you want to find the deflection at a different point, you would take that strain equation.
Yes.
Derive it with respect to the second.
Yes.
The second loading.
Yes.
And then set that second loading
equal to 0. Yes. That's a concept. Okay. So that is a new thing. I think this is a new thing, but I think this is the essence of that theory. Okay. And then here in the following, I'm going to show you how to, in details, how to implement these calculations. And that one basically is in parallel to these steps here. Okay, so we see. So again, we put into stage 1 and stage 2, and here, let me do this one here. So this is the P in stage 1. We apply the P slowly, so that is the diffractions. Okay, so in this slope 1 and that diffraction here, this is our diffraction. This value can be checked out from, again, using your appendix, the appendix I give to you. So this should be equal to P L cubed and 3 EI. And this is the point D. We keep in mind that's where we're interested. So in stage 1, we can build up the curve, and this curve will help us for calculation. So this is the diffractions at point A. A point is here, and D is here. Okay. So this is a loading at A. The other similar curve is diffractions at point D. This is the loading at D. Okay. So for this case, in the stage 1, we increasing the loading at A is slowly from 0 and then until it reach the value of the P we are given here. So this is stage 1. In stage 1, that corresponding to here, that is 0, because at point D in stage 1 we haven't applied the Q yet. Okay, and in stage 1 the distance, the diffraction we move is at point A. Diffraction at point A is given by this one. So, oops.
XAP.
Okay, so that is this one. This one, PLQ 48 EI. Okay? Diffraction at point A is this value here. Right now, this graph, I have two graphs.
Wait,
this
graph value, why don't they match?
This graph only documents the
Shouldn't
displacement.
it be 3,
not 48?
Oh,
Like,
3,
yeah,
yes,
like,
sorry.
why don't they match?
Sorry. You see, I got bathroom questions to Sarah. The answer to Sarah's question for that homework is 48. Okay. So back to here, and then in stage 1, and so if you like, we can document this one here. So this one in this way will be at the point D. So in stage 1, point D, that distance is given by this one, okay? And that one is not important because the loading is equal to 0, so contribute nothing to the strain energy. We don't have to find out this
Wait, why
one.
wouldn't you use the formula?
Yes, this is a formula here.
Yeah, I know. Like why? And then, but are you just saying that it's just so insignificant?
Here I show the method 2 is to help you to exercise using the example to exercise this process. But again, you didn't listen to
okay.
me. This method 1 will be the easiest one. Okay, so no, we'll keep on this one. Stage 2 is this, and stage 2 we begin to apply slowly the Q. So in stage 2, we increase slowly, gradually of the loading at D until it reach the magnitude we desire Q, and eventually we're going to set up to 0. So in this way, let me draw that here. Will that be okay? So this is stage 1. So let me draw this one. And stage 2 is here. So the application of the Q going to deform the beam, and in addition to this diffraction, let me draw using green line here. Okay, so from here to here will be curved, and then to this point, because you see the application of the Q, the influence of the Q to the whole beam will make this portion always a straight line.
It's just a
So here, if we found this slope at this point, say let me graphically show the slope here, then the contribution of the Q to the diffraction to the beam in this portion will be remain as a straight line. Okay? Okay, then we figure out the details here. What is this one? This one, again, we use our table, appendix D and case 1 for that case, the formula is this one, right? This one, let me show that here. So basically this one is equivalent to our case is Q and the EI, the length is L over 2. So we want to calculate the diffraction here. So that diffraction, if you look at the tables, the diffraction is P times the length of the beam, Q, divided by 3EI. Are we okay? Okay, so that one will be equal to how much? PL cubed and 24 EI.
And so that's the second part, right?
Yeah, for this one, because right now I'm picking up is the case 1, only this portion is curved. Okay, so I pick up this one. And then how about this one? From here to here, this portion is how much? If say this is the angle theta, yes, and then that can be approximated by, basically that is tangent theta times L over 2. But theta is a very small angle, so usually is we simply multiply theta by L over 2. And what is theta? Theta represent is the slope at here. That is the theta here. Okay? And look at the case 1. The theta represent is a slope. The theta is equal to P times the length of the beam square divided by 2EI. If you look at the middle columns, that is the information there. And we simplify this one. Theta equal to 8EI and PL squared times L over 2. So this is 16 EI PL cubed, right? Okay, so now what is this one? What is this one? This one will be this plus this. Can you see it? My drawing is not so perfect. This portions will be this plus this one, PL cubed 24 EI plus 16 EI PL cubed. Because you can see this portion, diffraction of this one is influenced by diffraction at this middle point, also influenced by the theta B angle pointing down.
So would there be 3 sections or just 2 sections? I mean, like, if you're going to draw it continuing on your graph at your P and Q graph.
Let me do this one here quick, carefully. So this portion represent, do I have to move? This portion represent, here again, this is a key. This portion represent is the diffraction at point D contributed by force Q. This portion is diffraction at point D contributed by force Q. So let me implement this one here. So that is PL cubed 24 EI.
But on top it's going to be that plus the other
This one
PL
will be
over
constant.
16, right?
The top one here will be equal to this one. And this one is how much? This one
That
will
plus
be
the
equal
61
to,
over 16.
yes, 5 over 48 PL 3 EI. This one is from here. This one is contributed by loading Q, happen at point A. So right now we're calculating 1, 2, 3, those terms basically equivalent is calculating x1, 1, 1, 2, 2, 1, 2, 2, etc.
And we said Q is equal to P before.
Q eventually will be equal to 0, and give me a few moments and I will show you that one. Okay, so let me continue.